but it sounds like it's all okay now. So yeah, I just want to introduce Huaiyu Yuan from Berkeley. So today he's going to talk about exploring the North American upper mantle using EarthScope data. And Huaiyu did his PhD at University of Wyoming with Ken Duker, and he finished in 2007. And then after that, he moved to Berkeley for a postdoc. And then last year, he became an assistant researcher in the Berkeley Seismological Laboratory. So I'm very happy that he can give this first webinar of 2012 for the TOG group and for an extended EarthScope audience. So for you.
Now, before we start, can anybody see any screen?
No, I can't. I just see the webinar viewer just saying it's with his photo and the title, so that hasn't come up yet.
Right. If I change presenter to Huaiyu, that should take us to his screen and then the presentation. So, Huaiyu, if you're ready, I'll switch control over to you.
Yes, please. Okay,
sounds good.
And also for the audience, you guys are welcome to ask questions. You can type questions in the little go to webinar control panel, and then we can, Andy will be able to unmute you at either during the presentation or at the end, and we can open it up for questions. Right now everyone's muted except for the four of us, but then we can open it up for questions afterwards. Thank you.
Yeah,
oh, now I can see the I can see the presentation now, so it's all working.
Okay, great. So Huaiyu, so what I'll do is, like Megan said, if anyone has any questions, please just type them into the questions box on the webinar window, and I'll either condense those during the end, or if you really want to make a personal appeal, we can unmute you and you can ask it in a colloquium. But for now, we'll hand it off to Huaiyu. Oh, Huaiyu, sorry, Huaiyu. It looks like you were muted, so I've unmuted you.
Okay. Oh, okay. I'm good now?
Yes, we can hear you.
Yeah.
Okay. So I also have my email address here. If you have questions, you can also send me an email too. Here's my talk. The title is really big. It's like for the whole continent and everything. But if you, I guess after you read my abstract, you'll figure out it's actually just our Berkeley regional tomography results. Did you see screen? I flipped the page. Did you see that?
No, it looks like, at least from my perspective, I don't see. There it is.
Okay.
Yeah, looks good.
Okay, I guess I need to turn off this panel thing. All right. So the presentation is really about our Berkeley regional tomography inversion. And here's the outline. I'm going to talk a little about our waveform modeling setup. And I will spend most of the time talking about the structure we observe from our models. But first, I have a very long list. I have a lot of people to thank for. First, I'd like to thank Karen Fisher's group at Brown University. We work together. They provided all the receiver function images in our papers and some of the slides in this presentation. And I also like to thank a lot of colleagues for sharing their data, their thoughts. And also, I thank Steve and Carl for providing their Proterozoic Laurentia structural map. And the folks at BSL who helped with the inversion setup and many of the figure preparations. And of course, the EarthScope program, and also the RSDMC and the Geological Survey of Canada. They provide data, and this is a NS-funded presentation, I guess, or project. So the big picture about the North American continent, assembly and evolution. there are many excellent papers out there, like the famous United Plates of America from Paul Hoffman and many others. Here I'm showing the structural map from Steve and Carl in their 2007 paper. They have nice movies and PowerPoint slides. Did you see the movement of the mouse? Like, this is my pointer. So they have, you can follow the link to get the movie and the slides. Here I'm going to show some key ones to show the processes. I guess the formation started early on, like late Archean and Paleoproterozoic, by the means of collision of Archean blocks, like all these gooey areas. And then another episodes, actually several episodes, is the accretion of juvenile terrains that add to the stable core from south, like all these color-coded terrains from the south. And I guess roughly around the end of Precambrian, the continent stabilized, but after that they are rifting going on from both sides, actually the western, southern, and eastern side of the continent. So this is really a fascinating region, a lot of ideas to test on, and EarthScope just provided, the USArray component of EarthScope just provided us a unique opportunity to study this. This is an old figure I pulled from Lara's webpage showing all the deployments. And near the bottom here, it's from one of the captions of their figure. It shows the purpose of this is to build a network of seismometers deployed across the U.S. to record earthquakes and provide high-resolution images of the continent, structure, and Earth's deep interior. So if we combine the effort from the USArray and all other permanent and temporary broadband stations on the continent, like all the sources from DMC, Canadian Geological Survey, Geoscope, will have over 20 years of broadband 3-component recording. It's showing on this map, it's over 2,000 stations. This is probably the most dense broadband coverage of the world. And we can, well, we started our regional inversions since 2004, along with the rolling of the USArray. You know, our group has a long history of developing global models, and in 2004 we decided to give it a try to the North American case. We applied the global technique to the regional case, and here these are some highlights of the techniques. We used 3-component waveforms, fundamental and overtone surface waves, and in particular we added surface wave splitting station averages as another constraint for anisotropy, and we inverted for isotropic velocity, radial anisotropy xi, and azimuthal anisotropy g for the upper mantle of the North American continent. Here is a slide I got from Scott. Basically, these are the data recording from one event here in North America and for a station in Eurasia. The top one here shows the phases we used Scott used in the global inversions. In my case, I'm only interested in the regional case. Like I use, say, for this example, only just the minor arc phases, like the Rayleigh wave here and the mixture of the body waves like S and SS here. These are the overtones. Some other aspects of our inversion. So we used Barbara's normal mode asymptotic coupling theory, NACT, for the inversion, both forward and the inversion part. This is a paper published in '95, a long time ago, but the theory is still going strong, and we have many excellent models. And you can see this theory actually gives nonlinear waveform sensitivity kernels. Like the figures here shows the bottom one shows the lob wave along the surface, and the top one shows the body waves, the SS phase. Like you can see finite width of the Fresnel zones, non-uniform sensitivity along the rays, and we used both fundamental mode and overtone data. You can see the kernel sensitivities from here. This is 60 seconds for VS and Radial Anisotropy. Xi, they peak at shallow depth, but 100 seconds, it's a little deeper. And if we include the overtones, you see the sensitivities actually goes all the way to the transition zone. So far, we have published 2 generations of models, and we're working on the 3rd one. I'll go through the details of these. So the first model was published in 2007. The purpose of this one is to close the gap between the global and local inversions. You can see from here, these is a map showing the global model nodes of our inversion, global inversion, and embedded are these red circles. That's the North American model space. We only invert for the structure for these red circles. And in our first model, we used the pre-TA stations. That includes about over 300 global stations, like all these blue triangles, and about 550 global events. The overall pass is about 60,000. The resolution, the resolution for our first model is around 500 for VS and almost 1,000 for Radial Anisotropy and Azimuthal anisotropy. The paper, the model was published in these papers. Here's one highlight of our first model. So basically, for the first time from the Azimuthal anisotropy inversion, we see a sharp transition in the fast axis of the anisotropy direction with respect to depth. Like here at 3 different depths, you see the fast axis directions changes from north-south kind of direction to the plane motion direction at, say, 300 depth. And the arrows here show the plane motion direction. So this is, I guess, also we have this plane motion, absolute plane motion, or APM parallel anisotropy direction. This is revealed for the first time by our first model. And then in 2010, our second model, we included the TA data, 4 years of TA data all the way to the end of 2008. So we reach better vertical and lateral resolution. Here's the setup. You can see it's much denser node spacing now. The resolution for the VS is about 250 kilometers. We have almost 1,000 global stations and almost 700 global events. The total pass, the number is 200,000. I'm going to talk about in most of the slides about our model 2 here, so I'll skip this one. And now we're working on the 3rd model, which has slightly different approach. We're aiming at the middle of the continental lithosphere, and we use different approach, and this is working in progress. I'll come back to this very soon. So this is our the 3rd model. You can see now we only use the regional and local events. And we have over 2,000 stations. The overall, the number of passes about 150,000. The resolution now is reaching 100 kilometers. To validate our models, in the first two models we developed quite a bit resolution tests, and these you can find in the papers. Here I will just show some quick tests for Model 3. Basically, we have a spectral element method package, and we can run our models through it and compare the data with the model predictions. For example, here, this is the 2009 Baffin Bay event. We chose this event and compared waveforms at these stations, like these green triangles. To the left, these are the Z component, and to the right, these are the transverse component. You can see the data and the spectral element synthetics are in blue and red. In most cases, they're overlapping. And for comparisons, which means this is very good fit, for comparison also showed the 1D synthetic, that's the gray curves. And last November we had the Oklahoma event, which is it's a good one because it's not too big to cause damages, but it's still big enough to provide coverage for the whole continent. Like the map here, all these triangles all have recording of this event, and the color coding here is for the waveform correlation between the synthetics, the RegSEM synthetics, and the data. So in most cases, we have very nice correlation. And to the right here are the Z and T components, waveform fit for some select stations, EGAK, FFC, and HOPS. Still, this event isn't in any of our models, any of our inversions, but we have pretty good fit between the data and the model predictions. And we can actually take this event and compare the data variance reduction, say computed from our three models, like the 2007 model, 2010, and the latest one. And the left panel here shows the variance reduction for Z component, fundamental Z component for this event. We see all our models do pretty good job with the variance reduction over 80%, and T seems we still have some job to do, but the trend is good. We're improving the fit. And again, for comparison, I showed the 1D synthetics, which is way down here. So in the following, how's my time? In the following, I'm going to show the results, mostly from the 2010 model. I decided to split this into three parts because it's really a big continent, and the first I'll have to just focus the continental-wide structure, and then I'll move to the western U.S. And in the third part, it actually has to do with our new model. I'll say something about Cratonic lithosphere, the MLD, mid lithospheric discontinuity, and some structure we see in the eastern U.S. Okay, so the first part, continental-wide structure. So this is published in 2010 model. I guess these are the highlights of the model. We see anisotropic lithosphere thickness boundary at about 200 kilometers beneath the Craton, and we see a layer cake kind of structure, anisotropic structure of the Cratonic upper mantle, and we see alternating negative side. Here I show VSV greater than VSH zones following the cratonic sutures, and in the end I will show some continental wide shear wave splitting equivalent two-layer model. So I guess I have to show the isotropic velocities for the continent. The map, two maps here, shows 150 and 300. Yes, first you can notice the big difference between the fast Craton and the slow western U.S. at shallower depths, and at deeper depth at 300. You see still see some high velocities, and our interpretation later you'll see these are, we associate these with the subducting slab or some of the instabilities beneath the Craton. The radial, another figure, this is going a little deeper at 400. The western U.S. velocity is dominant, and again, this is the subducted slab. And radial anisotropy is defined by the between the ratio of the horizontally polarized shear wave and the vertically polarized shear wave. So it gives the sense between horizontal shear and vertical shear. For example, the map here at 150, you see all these red means vertical kind of movement. They're associated with the subduction or rifting, like beneath the Rio Grande rift, and some of them you can follow the structural trend, like the trans-Hudson origin, and some of the sutures in the U.S. Another feature is the Craton side at 150 is bluer, which means horizontally faster than the western U.S. side, which is which shows more vertical sense of shear. And I can show couple vertical depth profiles. The first one here shows C to C prime. C to C prime. It goes from the western U.S. into the Cratons, and it crosses several sutures like trans-Hudson here, and some of the eastern sutures up here, probably still part of the trans-Hudson. And we see where these where this line crosses the sutures, there are structure like this. These are all negatives, or I mean vertical. How do I say this? This means vertically sheared wave, vertical sense of shear beneath the sutures, and across the other line from D to D prime, going from northwest to southeast. Again, see the sutures here, and here, and then we observed the perturbed radial anisotropy structure, which goes all the way in the Craton lithosphere. I guess this suggests all these structural maps, all these sutures from the early tectonic events still have their signature in the current upper mantle or lithosphere. The most fun part of our 2010 model is the Azimuthal anisotropy. Here, these two maps shows the shallow depth Azimuthal anisotropy, which is shown by all these black sticks with its length for anisotropy strength and its direction for the fast axis directions. And the arrows here shows the plane motion directions. Red is for the North American plate, blue is for the Pacific plate. So at shallower depth, 70 and 150, at 70, we see all kinds of directions like northeast, southwest, and north-south, and northwest, southeast in the continent, in the Craton part. And for the western U.S., it's more or less like this direction is the Pontifical plate direction here. This is very close to the North American plate motion direction. And offshore, you see the directions aligned to the Pacific plate direction. And another feature here is at 150, you notice a change of the directions from this crazy pattern to nearly north and south. So this is at 150. And in the western U.S., again, offshore it's still Pacific plane motion parallel, and beneath the western U.S., we start to see the rotating of the fast axis directions. Going back to the shadow structure, we actually noticed they correlate with the suture trends very well. For example, some of the sutures between Slab and Ray here, and between Medicine Hat and Hearn, Medicine Hat and Wyoming, and some of the sutures here, we have a northeast, southwest kind of suture strikes, and that's what we see at these locations. And also to the northeast corner, the sutures turn 90 degrees. They go like this now, and this is what we see there too. And also in the superior Craton, the sub-province structure all go east and west direction. That's what we see here in the superior Craton. And also if you see the Trans-Hudson origin, it goes like north-south, and then it turns to east-west up here. So a conclusion here is our Azimuthal Anisotropy model at shallow depth reflects the suture structural trends of the continent. And going deeper at 250 kilometers, we observed a consistency between the fast axis directions with the plane motion directions. Here are the plane motion directions I actually plotted two of them. One is in the hotspot frame, like all the red arrows for the North American continent, and blue arrows for the Pacific. And the other absolute plane motion model is the so-called no net rotation at R, which is shown as green here. We see most of the western U.S. and offshore and the western part of the Craton, these two plane motion models actually fit pretty well our Azimuthal and Anisotropy directions. However, in the eastern and central part, there's a big difference. And it seems the absolute plane motion direction from the hotspot frame fits the anisotropy a lot better, which I can show some statistics. This is the distribution between the fit of the hotspot model and the anisotropy directions. For hotspot model, it's nearly zero mean. However, for the no net rotation model, it's shifted. So this is in the Craton, and again in the western U.S., these two models seem to fit the anisotropy really well. Let me go back to this figure. So this Craton-wide anisotropy parallel to the plane motion actually gives us two applications. The first one, we can get an anisotropic lithosphere asthenosphere boundary map from this. So, for example, along this depth profile here, I show just the anisotropy directions. The bottom here, again, these are showing the plane motion parallel, which is all red. That's what we basically what we see just saw from the map. And the top we see these suture-zone parallel directions. So if we pay attention to this red line and compare this with the anisotropy strength of the whole profile here, that is summarized here by this plot. So basically, where we see these transitions, like up here and at 200 here, there's also a transition in the anisotropy strength. So basically, we can say put our LAB here, because first it shows the current plane motion parallel directions of anisotropy, and also it has this increased anisotropy strength that reflects the current plate shear. And if this is the LAB, then the rest, these two will be the lithosphere, and we can also draw another boundary here within the lithosphere, and I borrowed a term from Carnes Fisher, so this is now called MLD, mid-lithosphere discontinuity. And we can go through all the model points of our model and get a map of the LAB like this. So basically, the cratonic lithosphere is relatively flat, ranging between 180 to 240 kilometers, and this is actually consistent with many other studies for North American continent. Also, we can get a map of this intra or MLD feature that ranging from 50 to 150 kilometers. The second application here is we can address some of the debate on the SKS studies, whether the contribution of the SKS comes from the lithosphere or comes from the stenosphere. So first thing we can do is predict the apparent splitting parameters on the surface. That's the blue bars, and then the comparison with the data, the red bars, seems pretty nice. And then if we just assume our model is 2 layers, say we use the lithosphere as stenosphere boundary map to separate a shallow layer and a bottom layer. So basically this is equivalent to a 2-layer shear splitting model, and then we can have a continental-wide 2-layer model for the North American continent. And if we go into the details, compare these 2-layer model with some local structures, for example, beneath Harbor Station, Vadim has a very early paper. They show basically 2-layer structure there beneath the Harbor Station. The top layer has an anisotropy direction of almost east-west, and the bottom layer has the anisotropy direction that's plate motion parallel. And this is actually what we see here beneath Harbor Station. So this is the lithospheric layer. We see east-west kind of direction, and this is the stenspheric layer, or the bottom layer. That's the plane motion direction. Now, moving on to the Western U.S. I lost track of timing. Andy, how I'm doing? Andy? Anyone?
Sorry, I muted myself, Huaiyu. You have probably about 30 to 35 minutes left, based on the fact that we started a little bit late.
Okay, good.
Yeah.
Thanks.
No problem.
Okay, so now I move on to the Western U.S. part. Still, this is from our 2010 model. In this part, we observed sharp transition from the Craton, Western U.S., and we see the subducted wonderful curved plate in the transition zone depth. And our anisotropy model can actually explains this swirl SKS splitting pattern there. And I guess last point here I try to make is we try to address the deep anisotropy, and we like to associate with subducted slab. So this region is very nice. That's probably the best data coverage region in our 2010 model. Like here, these rose diagrams shows the azimuthal coverage, which is very nice for Western U.S. And the first thing from the isotropic velocity structure, we see a very sharp transition from the Cratonic North America to the Western U.S. following the Rocky Mountains here. And we also notice some structure like fast velocity between 100, 200 kilometers under Great Plains, and we see very slow ridges. And Colorado Plateau is relatively neutral in velocities, so is the coastal ranges. And the basin and range is very slow, and it goes down to 250 kilometers. One feature of the isotropic velocity is this high velocity structure beneath Oregon. So here I'm viewing from the model from northwest. So Washington is here, Oregon is here, and we see this blue fast velocity feature that goes from 250 to below 400 in our model. This feature correlates with many local tomography studies, and people all point to this and say this is the subducting and subducted slab. The azimuthal anisotropy of the Western U.S. is crazy. For example, you see here at 70 kilometers we have a sharp transition from the Craton side to the Western U.S. side. And at 70 we see all North American plate parallel directions. That's the blue arrow here. And then here this shows the Juan de Fuca plate motion direction. That's what we observed here. And at 100 depth it's more or less the same. And also I forgot to mention the offshore region, it's kind of parallel to the Pacific plate motion direction. And going to 150, the pattern start changing, and it's no longer this plate motion parallel at shallow depth. Now you can see probably a little bit swirl pattern here. And again, we still see a little bit of the Juan de Fuca motion direction and very strong Pacific plate motion direction offshore. At almost 200 kilometers, the whole pattern changes again. Now it's more or less the Pacific plate motion direction, say if I predict this into the Western U.S. And at deeper depth, say at 300 and 400, it's still this Pacific plate motion direction parallel, except at least depth, we see some east-west kind of direction beneath Oregon. And putting all together, this is a very depth-dependent model. And one nice feature about it is we can predict the surface shear splitting, apparent shear splitting observations, and that seems to follow this circular pattern of the shear splitting first observed by Savage and Xian. So this idea was first proposed by Savage and Xian. They noticed in Nevada there are lots of splitting nodes, but surrounding it you see this circular pattern of the splitting, and they call this the circular pattern, and or the other, I guess people also call this as the swirl. And it actually was observed earlier can say 98 paper by Schott and Humphreys, in their paper, you can actually see this swirl pattern a little bit. And also with the TA data, I guess you can still see this pattern. This is from Liu paper in 2009. Nevada is here, and you see this circular pattern, and this most recent paper from Richard's group. Nevada is here, and again you see the circular pattern. So if there's many models for this, including active upwelling, passive edge flow or toroidal flow, and also lithospheric drip for that. But if we just predict the surface show a splitting pattern, we can see a very good correlation. So here again, the black is our model prediction. We have almost, I guess, probably 75 to 80% of this circular pattern, with now somewhere here in eastern Nevada. The worst region is along the western edge of the Colorado Plateau, where local studies show a very sharp transition in both velocities and the fast axis direction change within 100 kilometers. Yes, we don't have the resolution there yet to finish the whole circle, but overall our fit to the surface circular pattern is pretty good. And here the figure here shows the angular difference between our predicted fast axis and observed shear wave splitting fast axis. It's nearly zero mean with about plus minus 15 degrees error, and the means of the splitting time is actually going to the negative side, which means our model is still underfitting the data, and we still need to boost the amplitude of our model a little bit. One last feature of the western US I want to point it out is this little guy at deeper depth. It has this east-west kind of fast axis directions. And remember I showed this high velocities below under Oregon between 200 and 400 kilometers. And if we look at this using depth profiles, that's these 4 profiles going from north to south. These are the velocity perturbations. We see this region here that has the high velocities all the way from 250 into the transition zone. And if we put the anisotropy direction side by side, again north to south, we see, so the direction here, the red and pink is more like east-west directions. So we can actually see a pretty good correlation between the high velocities here along the profiles and the east-west direction there. We speculate this east-west direction may be from the slab, and there are many models to show slab can be stagnate in the transition zone. For example, here's one for North America. So one profile going from Baja California all the way across the continent. The model shows nice features of the slab in the transition zone. And the model shows during the slab retreating, young slabs cannot penetrate the 660, so they ponder in the transition zone to form some structure like this. And we figure probably this is what we see in the western US too. So basically we have this stagnant slab which gives some forms of anisotropy, structural anisotropy at deeper depth. And then going up, we see some circular pattern at shallower depth, and then near the bottom of the lithosphere thin foundry, we see a very strong plate coupling. I guess I'd like to show this. I think this is stagnant slab feature. Is really nice. We see this in the Western U.S. and globally. This is a model from our groups from Scott's most recent model, which shows isotropic velocities at 500 kilometers. In the blue here, you see all these blue features more or less follow the trench on the surface. So the trench will be these dashed black lines on the surface. And also the circles here, the purple circles here are the deep events, like deeper than 500 kilometer events. They seem to correlate with the high velocities very well. So here in South America, here, Eurasia, Philippine Plate, Indonesia, Tonga, and even in the Mediterranean. So this is, I guess, one thing we like to look at in our global azimuthal anisotropy inversion. Okay, the last part is about the cratonic lithosphere and this mid-lithospheric discontinuity feature. The motivation, this is more or less from the results of our current ongoing modeling. The motivation of this project actually comes from the observation of this layered anisotropic structure in the Cratons. Again, this is the LAB here, and then within the cratonic lithosphere, we see this nice transition of the fast axis directions around 100 kilometers, and these dots are the negative residual function, negative phase from various studies, and it seems they also occur at 100 kilometers. And indeed, 100 kilometers is really a fascinating region in the Craton. There are a lot of things going on, like say first that the geological modeling and geochemical modeling will say this is the transition from depleted upper lithosphere layer to less depleted lithosphere bottom layer from, say, from Griffin et al. Paper. And this is also the green layer or viscosity very strong layer from Cooper et al. Geodynamic modeling. This depth range is also very close to the bottom of the effective elastic layer of the Cratonic North America from the modeling of Audit and Bergman, and not to mention residual functions see a lot of negatives at this depth. And also in the global tomography, there's little kink of low velocity at 100 kilometers. That's from Lackey et al. 2010 paper. And locally beneath the slate Craton, really wavy modeling also show this very nice low velocity feature at 100 kilometers. And again, going to global, long range active profiling shows this discontinuity, and which can be attributed to the low velocities around 100 kilometers. And there's also from the magnetotelluric studies, the high conductivity layer at that depth. And yes, people will argue this is also other things going on, like drop of water capacity at that depth. Like David Green will say this is the breakdown of the pegosite there. And not to mention there's still this kimberlite layer, accumulating of kimberlites at 100 kilometers due to the kink introduced by the water and the CO2 at that depth. So I'm not going to show all this here. I just show some quick results some quick correlation between the receiver functions and surface waves. So here, these are Cratonic stations, the 4 of these Cratonic stations. To the right, each subpanel here shows the receiver function, stacks of like over hundreds single shear wave receiver functions from Heather's group. They all show this very large negative around 100 kilometers. And to compare that with our Anisotropy model, we have for each station the fast X directions as the blue, and the anisotropy strength here, and we see the transition from different domains at all these stations. So there's a very strong correlation between the receiver functions and the surface wave anisotropy model, and also to the eastern edge of the Craton, some P-wave receiver functions by Vadim 11 also shows. So basically here, these are 3 stations: Harvard, PAL, and SSPA. The left is the radial P-wave receiver functions. The right is the transverse P-wave receiver functions. And highlighted here is this transition of the polarity, or the polarity flip. So for the Harvard station, it's here. For the other 2 stations, you see it gradually rotate from east-west direction to more like north-west and south-east for the other 2 stations. The point of this is this occurs about 10 seconds, and which translates into about 100 kilometers in depth. So there's a lot of things going on at these depths, and we try to, in our new model, we try to focus just the shallow part of the lithosphere. We are able to use a nice regional spectral element package to do the forward modeling, waveform modeling. So this is from a paper impressed by Paul. You can find more details from his webpage, including the whole package. And the RegSEM, this shows a chunk we used in our inversion. The color is the shear wave velocities along the meshes, different sides of the mesh. And this is a very nice package. It deals with anisotropy, attenuation, 3D structures, and 3D discontinuities like moho. And we also use a different approach. Instead of using the global dataset and global stations, we just use the local events, regional and local events, and stations. So here, these are our event coverage, which is very nice, almost 360 degrees. And the station, the total number here is over 2,000. The total path is 150,000. The project is still ongoing, but we have some nice features. And well, let me start from here. We have a nice study model from our global inversion group, which is developed using 60-second data. And here we're trying to push to 40 seconds. And using the global model, we can predict very nice starting waveforms, like the difference between the real data, 40-second data, the blue, and the RegSEM synthetics from 60-second model seem to match very well. So this is for FFC station and another station, PAL. And we have some preliminary results, but the first thing I'd like to look at is this MLD. So here, this is a map at 150 showing the isotropic velocity variations, and I drew a profile starting from the Oklahoma event all the way going north. That's from here. I guess this should be, sorry, the numbers here are not right, but basically this is from south to north. So from here to here. And then we see this nice cratonic feature that goes all the way to 200 kilometers. And nicely, this low velocity kink within the high velocities. I guess this is one feature we expected. And I still need to look more for the other regions. But I guess we're getting there. Time is almost there, and I'd like to show some results. Oh, I forgot to mention, also along this profile, it's not only the velocities showing this negative, the low velocity feature. There's also a transition from the radial anisotropy along this step too. So there is something going on there. And our maps, because the TA is almost there to the east coast, I'd like to show some results from our new model. So these are maps at 100, 150, and 200 kilometers. For isotropic velocity variations, the first feature I'd like to point out is the thick Craton. You can see that at 100, 150, and 200 kilometers. So it goes all the way at least to 200 kilometers. And then we see on the other side, offshore, this nice Atlantic feature that is very strong, very high in velocity at 100, and you can still see it at 150, but it's not there at 200 kilometers. I guess this is very old oceanic plate. So it's like over 180 million years, so probably it makes sense to have such a thick oceanic lithosphere there. And we'll see the transition from the Craton to the Atlantic. Craton to the Atlantic follows the structural trend. And also, we notice some features like starting from the Bermuda hotspot, there's some low velocity trend going on like this, which follows the hotspot track proposed by Miller et al. Of course, I guess Morgan would turn this track way up. Yes, it goes like this and turn up from here somewhere. Another feature is this, the upper one, this trend, the Great Media hotspot track. Seems we have a nice correlation from the velocities. You can see it cut through the Pacific, the Atlantic plate like this all the way, and it goes into the continent. The inland part was first observed by Fauci et al., and now we see this feature continues all the way following the New England seamount. And there are other features. I guess I have to pass this one. And one thing I need to mention is beneath the hover station here, the P-wave receiver functions is a very sharp LAB at 100, near 100 kilometers. And I guess right now we see the lithosphere there is really eroded by the hotspot track. So beneath the hover station, I guess for the first time we may say our surface wave model have a very strong correlation with the receiver function LAB in this region. And lastly, this MLD feature, to some people, it's a very interesting feature, but some people think it's a little confusing. For example, this is profile from David's paper, 2010 receiver function paper, going from C to D, C to D. It shows the receiver function stacks. And marked here are the negative velocity zones. And here in the western US, this is labeled as LAB, and in the Cratonic side, this is labeled as MLD. So people, well, people thought this is the same depth. Maybe there's it should be all the same, either MLD or LAB. And a recent paper impressed by Kumar et al. From Rina Kent's group, they show the P-wave receiver functions, CCP imaging for the whole US. So basically, they use all the TA data, all the permanent stations, and then they form two profiles, P1, that's the top one, and P2, and they see a nice continuous feature around 100 kilometers. It goes all the way from the western US to the eastern US. And then they like to put this as the LAB, which is at 100 kilometers. Their argument is, well, this is because of the water thing. The decrease of water solubility at 100 will cause melt and low velocity. That's what they see from the receiver functions. And from this diagram, I forgot to put, this is from David Green's paper. So at 100 kilometers, this is where Hagasite breaks down. So you have more water up there, and here you have less water. So it's easy to form melts at this depth. And then they argue this is just the bottom of the lithosphere. Well, simply we just compare that with our tomography model. This is still the 2010 model in the background, velocity variations. So we see in the western US there is a transition from high velocity lead to low velocity. So no problem, this is the LAB. But in the Craton side, you see the negatives are all in the middle of the high velocity. So it's hard for us, at least for me, to believe the asthenosphere to have such a high velocity there. Okay, I guess that's all I have. And to conclude, I guess this is from the USArray figure caption. It seems the USArray is doing a really good job. It benefits the community. We have many exciting results from surface waves, body waves, receiver functions, and spatial wave splittings. And specifically in our study, we observed anisotropy. Well, I should say this in other way. The fossil structures are preserved by the means of anisotropy, and the anisotropy also shows present time tectonic events, and we have a nice lithosphere, cratonic lithosphere that goes down to 200 kilometers in the Craton, and also we have a very fascinating mid-lithospheric discontinuity feature there around 100 kilometers in the Craton. And this is all I have. Thank you all.
Thank you very much, Huaiyu. We don't have a good way to simulate applause on here, but yeah, I'm sure everyone really appreciated this. And
thanks.
I want to encourage everyone to, if you have any questions, feel free to type them into the window. I got several during the talk, and so I'm just gonna. So if we have time for questions, I'm gonna dictate these, and then you can answer them as you can.
Okay.
The first question I got was from Januka Atanayake. I hope I got that right. It was a question early in the talk about the variance reduction of the two different components. And so her question was, why is the Z component, why does that have a better variance reduction than the T component? And then the sub-question of that was, is that an indication that 125 kilometer resolution is still insufficient?
Mm-hmm. Okay, so I'm not sure if I think I can go back. So for the misfits, I guess it's this figure. Why the T component is worse than Z? Mm-hmm. Well, we're doing surface wave modeling, and for surface waves, the T component is really sensitive to the shallow structures, like all the crustal structures and say the morphotopography and the shallow upper mantle. So to do this, we have basically we are doing long period modeling, and we don't have much resolution in the shallow part, say in the crust. So we have to use some good models, like say from either crust 2.0 or using some crust model, say from Rich-Waller Group's data set. We can do some dispersion modeling to form a very simple crust. So the problem there with the T may be part of, because of this, you know, we do need a nice 3D crust model to get a better fit here. But on the other hand, it's going to be a lot of computation, especially for SEM. If it goes super fine structure, it's going to take forever to do it. And for the other question, 150 kilometers is, yes, we're doing now.
125, if that was.
Yeah, 125. That's roughly 1 degree. That's the node spacing of our finest. I guess that's the Model 3. Yeah, I don't have a plot to show. Okay, this one. So these center ones are all 1 degree. 125, yes, guess we're getting there. We started from 800, and we have 400, 200, something like that. So I guess sometime. Right now, 125 is, we feel it's pretty good now. I don't have time to show other figures from the most recent model, but we do see some features like at 100 kilometers, we see this very, very narrow high velocities along the western US coast. That's the subduction, the current subducting slab, which we didn't see before, but now even with this 150 kilometer node spacing, we can see that a little bit. But yes, we are going to include, I guess, going to higher resolution, but again, it's going to take a lot of computing power to do this.
Okay. A related question on the T waveforms. This is from Robert Busby. He asks, it appears that the T waveforms have the right shape, but data is delayed in time from the model. Is that an indication of anisotropy not quite right in the model, or you might have already answered that with regards to the shallow structure?
Yes. So I guess so here I'm just showing the waveform fit between in the regional case, and in the global case, that's pretty much similar. We see a much nice fit to the Z component, but less good fit to the T component. As I mentioned, probably it's due to the shallow structural crustal structure. So yeah, the phase delay and sometimes the amplitudes, yeah, may be part of that reason.
Okay. There was a question from Bob Stern. He had several questions related to some more of the structural interpretations that you were doing.
Okay.
And so one of the questions was, is vertical structure not seen beneath the Grenville province? And then sort of a follow-up to that, is there any evidence of any kind of orogenic fabric underneath the Grenville area?
Grenville, okay. I guess I could maybe show this figure. Sorry, what's the question again about the vertical?
The question was, did you see any sort of vertical structure underneath the Grenville, and then also related to the Grenville, did you see anything that might have been like an orogenic fabric?
Orogenic. Well, we're still, so that would be part of our Model 3 modeling, and I guess this figure here shows there's some transition between the Craton and the Atlantic, between the two plates, and it seems the structure, the surface structural trend is like this, right, highlighted by the dashed line. So I guess we see something, and I need to dig more on this, say from the radial anisotropy side, and also when we get to the azimuthal anisotropy side. Definitely there should be some structure there.
Okay. There was another question from Bob related to the nomenclature. So the MLD is the mid-lithosphere discontinuity. Is that equivalent to the quote-unquote what would be the Hales discontinuity?
That's a good question. Yes, I forgot to put it here. So people talk about Hales or Gutenberg discontinuities. They also occur around this depth range. So I don't know. The answer is I don't know whether this MLD is the Gutenberg or the Hales, but well, there are a lot of things going on there. So maybe.
Okay. And there was one more question from Bob that was from earlier in the talk, and if I don't phrase this right, because I'm a little uncertain about what exactly he means, Bob, you can just re-ask it if I botch this. But his question was in Western North America, you're interpreting structure around 70 kilometers as North American plate, but Pacific plate at greater depth. So I'm not exactly sure what that question is asking, but maybe you have a feel on that.
I guess I have to ask you to rephrase. What?
Okay.
Sorry.
Yeah, maybe I can just have Bob rephrase that one if he's still curious about that. The next question was from Januka, and that was referring to the Thibault and Pershuk paper from '97. Their interpretation of the 100-kilometer low velocity zone that you talked about later was because that there was an introduction of partial melt in that area. And so I guess what would your take be on that? And are there any sort of complementary models of attenuation that would support that?
Well, let me get to the attenuation part. For receiver function, so this is really a thin layer. Receiver function can see it. Our early models didn't see that, and now we start to see that using very high resolution models. But still, it's pretty faint structure, at least to the say the tomography. Attenuation is even harder to do. I guess maybe there's some feature that people can do about this. Say something like triplication, and if people can model the attenuation part of it using very high resolution, very high frequencies. But I guess for tomographies, probably the answer is no. But certainly there's some other techniques that can be used here. For the first question, the melt there at that depth, yes, in their paper they proposed that's because of the overlapping, say, from the Craton geotherm with the kink introduced by by water and CO2 there at I guess 100 kilometers again. So I guess that's still part of the explanations for this feature, MLD feature, and I guess I don't know. It's not probably some other people would like to say about this. I guess
okay.
My short answer is yes, it's consistent, and yes.
There were a couple questions about the availability of this talk afterwards. One of the technical issues we had at the very beginning was trying to make sure that we were able to record both the video content and also the Huaiyu's narrative to go with the talk. If that worked, we'll post the whole thing through the EarthScope National Office website somewhere soon down the road. Otherwise, we might be able to make a PDF or a PowerPoint of this available. So there was a question from a couple people in the audience that I just wanted to follow up on before we got any deeper. We have a question from Steve Gao related to the anisotropy that you were interpreting.
Okay.
He was curious about the cause of the north-south directed anisotropy between the mid-lithospheric discontinuity and the lithospheric asthenosphere boundary beneath the Craton.
Okay. So the north-south direction of the anisotropy.
Yes.
Okay. So what's the question again? So.
What would you interpret as a source or a cause for that fabric direction?
Well, when we tried to publish paper, this question was there already. So we tried a lot of things. The first thing we thought was, well, very obvious. If we have, say, the current plane motion like this that leaves the signature beneath the lithosphere, and then could this be some fossil plane motion? And indeed, I looked around, say, all these paleo plane motion reconstructions. For North America, it's since Precambrian, has been traveled all the way from south to north to the current position here. It seems there's quite some relative north-south movement of the continent. So that north-south continent movement could I guess give some frozening anisotropy, at least. That could be part of this, but there's no I guess quantitative measurements for that. So it's still a speculation. And other things to explain this is, so this is in the bottom of the Cratonic lithosphere, and currently we have the, say, the ridge push, maybe, and the subduction. So the stress buildup may be able to do something to this kind of softened bottom of the lithosphere. I'm not sure this will work not, but I guess during some early discussions, people told me that could turn the, at least say the fast axis observed into perpendicular of the current maximum stress. Other explanations, well, again, this could be fossil structures. There are episodes of paleosubductions going on. So that goes like east-west direction. That can probably push and form some a trench parallel kind of a frozening anisotropy. I guess that's pretty much I have. There's no, I guess it's still open, and I'd like to welcome other thoughts about this.
Okay, thanks. And we have a question from Robert Busby relating to the latest results that were presented that you showed from Kumar's work.
Mm-hmm.
And his question is, there appears to be much higher variability in the eastern United States and North America at depth compared to the west. Do you expect such an increase in variability?
Yes, this is just the difference between if you use TA or if you don't have TAs, they just use the permanent stations. I guess you can just look at the map here. It's very coarse. It's a very large spacing. That's why you see all this structure like this to the east. Mm-hmm. Well, on the other side, the western, I guess the middle part of the US, you have the TA coverage. That gives you this continuous feature. So you do have a lot of stations. I guess by the end of 2014, you have, I guess they will have probably something like this to the east.
Mm-hmm. Okay, great. I have a question from Luciana Astes. In most of your examples, you showed data from permanent stations. How are the fits of TA stations? Also, I want to ask if you can see delays around station H17A, which is located in Yellowstone.
H17. Okay, the fits to the, I think I have one station, the TA stations. Well, in general, the quality of TA stations is very nice. Sometimes it's, I guess, it's better recording than the permanent stations, but it's kind of short. It's just 2 years.
Mm-hmm.
Let me see if I have. No, these are all permanent stations, but the fits to, I guess, for these at least some of the TA stations are, it's at least as good as these ones.
Okay, great. The TA operators.
H71A, so that's the Yellowstone station.
Yes.
So here's what we do in processing data. We collect data from DMC, and then we compute a very simple 1D synthetics, and then we compare this with data. If the comparison is good, we keep the data, and then if it's not, it's thrown away. So later on, we can use 3D synthetics to do this data picking, but in general, this is all an automated process, so I really don't know about the station. Sorry.
Okay. But in general, do you see any delays around Yellowstone, or is that?
I'll have to look, but also remember we're doing very long period modeling, so probably will be very small. I mean, even if there is something, a couple seconds or so, I won't be able to see it.
Okay. Last question is from Fanchi Lin, and that has to do with the circular pattern of SKS splitting beneath the Great Basin in the western U.S. And it's a chicken or the egg question. So it's can the circular SKS pattern in the west be predicted by the surface wave model all along, or is the circular pattern that's predicted simply a reflection of the input of the SKS data set?
It's a good question. We actually had some discussion over this a long time ago. So in general, surface waves have very good sensitivity down to like about 200, 250 kilometers. And I guess if we just look at our Western US model like this, if we just use surface wave model, we'll see pretty much the top panels the same as the inversion using both surface waves and the SKS dataset. The bottom side will be, if it's surface wave, a long dataset, very small in amplitude, and I remember I do see some consisting features like these, and the Pacific parallel features like this, but in very small amplitude. One thing we didn't see is this east-west kind of direction. That's not from the surface waves. But, well, I guess I can also talk about resolution issues. You know, this very broad spacing, 500 kilometers or so. And we'll see if now we have finer grids, and we try to use multiple frequency bands, and hopefully, I guess we'll see pretty soon whether we'll just see these features from surface wave standalone inversions.
Okay, great. That was it for our questions. If no one else has any questions, then I just want to extend our thanks to Huaiyu again for taking the time to not only give the webinar, but also to withstand the technical difficulties at the beginning, and then to take so much time to answer questions afterwards. So thank you very much, Huaiyu.
Oh, thank you, Andy, and thank you all.
Yes, and thanks to everyone who came, and we will do another one of these soon, and you will be we'll send out a notification through the Iris bulk mail and other listservs. So stay tuned.
All right.
Thank you.
Yeah. Thanks
Thanks
everybody.
again.